Welcome to the Newton's second law video. In exercise 1, we'll be testing Newton's second law by using a hanging mass to pull a cart, plotting force versus acceleration, and comparing the slope of that graph to the directly measured mass. If you are using a blue high-resolution force sensor or a black force sensor, you will need to calibrate it. The normal resolution force sensors may skip this step. To calibrate the sensor, start by weighing two different masses, including the hanger is easiest. You will also need to cut about a meter length of string. The exact length isn't critical as long as it allows sufficient cart motion. Attach the force sensor to the cart using the supplied long thumb screw. Plug the force sensor into the data acquisition interface. Add a cross piece to a retort stand and hang the sensor from it. It doesn't matter if the cart is attached during this process or not. You'll need to know the weight of each of your calibration masses in newtons, which can be easily calculated using Excel or whatever method you find convenient. At that point, open the capstone file and click the calibration button at the left-hand side. Capstone will lead you through the process, but you need to select a force sensor and a 2-point calibration. You should also press the tare button before hanging any of the masses. Hang the first mass, enter its weight in newtons, and click the button reading Set Current Value to Standard Value. Repeat this process for the second mass and click Next. You may now click the calibration button again to close it. If you have to close capstone for any reason, you should recalibrate your sensor. Set up the apparatus as shown. Start by adding the clip to the side of the track. Note that you must slide the square nut in from the end of the track to do this. Also, put it over a retort stand and tighten it in place. Next, add the rotary motion sensor mount to the other side of the track, with the sensor itself hanging over the end. Add an end stop to prevent the cart from running into the sensor. Finally, add a foot to the other end of the track. Don't forget to plug the rotary motion sensor into the data acquisition interface also. Level the track as best you can by measuring the height at each end of the track. You can adjust either end's height as convenient by either turning the feet or loosening the track's clip and sliding it up or down the retort stand. Place the cart on the track and hang the string from the force sensor over top of the largest pulley on the rotary motion sensor. Attach the mass hanger and a 10-gram mass. Make sure that you have measurements of each of the total masses you apply to the cart. Press record in capstone and pull back the cart. When you release the cart, try to hold the force sensor's cable so that it doesn't pull on the cart in either direction. That portion of the graph should be linear. If not, you may need to repeat that run. Press stop in capstone. Repeat this process, recording at least 3 trials before changing the mass. Add another 10 grams to the hanger, again recording the total mass. Record at least 3 trials for at least 5 different masses. In exercise 2, we'll be angling the track. We'll repeat what we did in exercise 1 with the mass, but this time we will also use the intercept of the force versus acceleration graph to find the angle of incline and compare it to a more directly measured value. First, angle the track by loosening the track clip, sliding it up the retort stand, and tightening it again. Next, take some measurements so that you can find the angle. There are various ways to do this, but I recommend picking 2 points separated on the track diagonal by a convenient value and measuring the height at each of those points. Add an end stop to the lower end of the track to ensure that the cart doesn't go flying. Find the smallest mass that causes any acceleration at all. Note that you will need to hold the force sensor cable during this process. Try to find this value as accurately as possible by using the smallest mass increments available. You will be adding to this mass in 10-gram increments. After recording the mass already applied, add the first 10 grams and measure the new total mass. Just like we did in exercise 1, hang the mass from the string, press record in capstone, pull back the cart, hold the force sensor cable, and release. As before, after release, there should be a section of graph that is approximately linear. If not, you may need to redo that run. Once again, take at least 3 trials each for at least 5 different masses. Thanks for watching the Newton's second law video, and remember, if you want your physics lab to go by faster, just apply more force.